Hello everyone. So before moving ahead in this chapter, we need to know some basic terms and some classification of elements. Okay. So let's start with these three terms: branch, node, and loops. So while studying this chapter, you will get to see these terms much often. Okay. So what is a branch? Like branch represents a single element. It can be resistor, it can be voltage source, it can be current source, it can be capacitor, it can be inductor, anything. But between two nodes, there should be an element. Okay, it can be anything. It can be independent or dependent, voltage source, current source. So here, if you see, what are the branches? This is branch 1, this is branch 2, this is branch 3, this is branch 4, this is branch 5. So these are the 5 branches. So I will represent B as number of branch. Okay, B as number of branch. So how many branches are there? 5. Let's talk about nodes. So what are the nodes? Interconnection between two or more branches. Like this is one node, node A, this is node B, this is node C. So I will represent the number of node as L. N. So what are the number of nodes? Number of nodes. Number of nodes are 3. And then loops. So what loops you can see? This is loop. This is also a loop. This is also a loop. Okay. So how many loops you can see? 1, 2, and 3. But someone will say like this is also a loop. Yeah, it's a loop. It will be called a loop. But this is not an independent loop. Because in this loop, you can see there is one small loop also there. Let me make a clear diagram. If we talk about this loop, okay, 5 ohm, 3 ohm, and 10 volt. About this complete loop, you can see there is one small loop also there. 5, 2, and 10 volt. So this loop is not an independent loop. Okay. Not independent. Not independent loop. Okay. This is known as independent loop. Independent loop. Okay, so here that L, this L represents independent loop. Okay, L is not the number of loops, independent loops, number of independent loops. So how many independent loops are there? 3. Okay, yeah. So now this formula is there. You don't need to mug it up. B equals to L plus N minus 1. So here you can see L plus N is 6 minus 1. So branch is equals to 5. 5 is equals to 3 plus 3 minus 1. So here you can see the derivation of that formula here as well. So what I need to deliver here is that you need to know what are nodes. When I say while delivering the lecture, when I sometimes say node A, then you should know what I am talking about. This is node A, and this is a branch of 5 ohm, 2 ohm, 3 ohm, 2 ampere, 10 volts, and this is a loop. This is an independent loop. Okay, this is also called a loop. This one also is a loop, but this is not an independent loop. This is a dependent loop. Okay, so there are 3 independent loops: loop 1, loop 2, and loop 3. Okay, so these are basic terms. I hope you understood it. Now we will move to some basic laws. So KCL KVL in 11th or 12th class you must have studied it, but let's revise it once again. So KCL. So what does KCL say? The algebraic sum of all the currents entering into a node is 0. Okay. So let's take an example. Let's call this one as a node A. This is a node A. This node is node A. Okay. So let's just assume there is I1 current is entering here, I2 current is going out, I3 current is going out, I4 current is entering, and I5 current is entering. Now forget about the law and everything. I will just tell you how to write the expression. Okay. So what we will do, we will take outgoing current as positive. I will repeat it. We will take outgoing current as positive and incoming current as negative. बाहर जाती हुई करंट को पॉजिटिव लेंगे, अंदर आती हुई करंट को नेगेटिव लेंगे. Let's call this one as node A. So let's apply KCL at node A. KCL at node A. Outgoing current as positive. What are the currents outgoing? From node A, what are the currents outgoing? I2 is going outgoing. plus I4 is I3. This is I3. This is I3. I3 current is going outward. Now what are the currents incoming? I5 is coming incoming. I4 is incoming. I1 is incoming. Equals to 0. Okay. So basically I2 plus I3 is equals to I1 plus I4 plus I5. So what analogy did I give you? Well, while I was teaching you the concept of current, water flow, right? Water flow के हिसाब से समझाया था मैंने कि पानी आता है और इस तरह जिस तरह H2 मूव करता है तो पानी मूव करता है, वैसे ही अगर चार्ज मूव करते हैं तो करंट फ्लो होती है. In the same way, let's assume I1 water flow is coming here and I5 water flow is coming here, and then that is getting out in I2, I3 and I. Okay, I4 is also incoming. I4 is also incoming. So basically it would be plus I4 equals to I1 plus I5. Okay, I2 plus I3 plus I4 equals to I1 plus I5. So I1 is incoming, I5 is incoming, I4 is incoming, and that is getting out in I2 plus I3. Are you able to understand? I1 is incoming, I5 is incoming, I4 is incoming, and that is getting out in I2 and I3. Okay, like let's assume this I1 is getting incoming, I2 is getting incoming from here, and I3 is getting out. So how will you write? I1 plus I2 equals to I3. Did you get it? Did you get my point? Or what you can write? We will take outgoing current as positive. So I3 will be positive. Incoming current as negative. So minus I1 minus I2 equals to 0. So I3 is equals to I1 plus I2. That's how you can also write. Okay. This you need to remember. You take outgoing current as positive, incoming current as negative. Okay. So while doing the circuit analysis, it will be very, very useful. So that's how you apply KCL, KCL. Now we will study about KVL. Okay. Very basic it is, right? I guess we will see some example here. Yeah. So let's solve this example. You need to tell me the value of I. So what we will do? Outgoing current as positive. 4 plus 2. Incoming current as negative. What is incoming current? Minus I minus 3 equals to 0. So what will be the value of I? I will be 3 ampere. You can check here as well. 3 ampere current is coming here. 3 ampere current is coming here. So 6 ampere current is getting out in 4 ampere and 2 ampere. Right? You can clearly see in the diagram. 3 ampere current, 3 ampere current, 2 and 4. Now solve this question. Let's solve this question. Incoming current as negative and outgoing current as positive. So only outgoing current is 5 and incoming current are I1, 2 ampere and 4 ampere. So, okay, so I is coming out to be minus 1 ampere. What do you understand by this? I is minus 1 ampere. So what do you understand? The direction shown is this, but in reality 1 ampere current is flowing in this direction. So you can see 2 ampere current is coming incoming and 4 ampere is also incoming current. So 2 plus 4 6, and that is getting out in 1 ampere and 5 ampere. 2 ampere coming, 4 ampere coming, getting out in 1 ampere and 5 ampere. 6 ampere is coming, 6 ampere is getting out. So here also you can see, right? So this is the concept of KCL. So I hope you will be able to apply the KCL now, right? Now moving on to the KVL, Kirchhoff voltage law. So forget about the statement. Statement just say the algebraic sum will be equals to 0. Now I will tell you how to apply it in the circuit. Okay, no one will ask you the statement or anything. How to apply it in circuit. So what you will do, you will first take a ground. If there is a circuit given and there is no ground mentioned in this circuit, initially there was no ground mentioned, right? So if there is no ground mentioned, you can take any arbitrary ground. We will try to take arbitrary ground near the voltage source. We will try to take the ground near the voltage source. Voltage source के नजदीक ground लेना है हमेशा. तो ये वाला voltage source है, इसके नजदीक ground ले लिया. Then what we will do? We will start from here. We will start from ground and then jump. From 0 to we jumped above V1 and then we will look backward. Jump and look backward. Jumped here and look backward. What is the sign? Positive. So we will write positive. Now from here we will jump and look backward. We jumped here, look backward. What is the sign? Negative. Minus V2. Jumped, again jumped, look backward. What is the sign? Negative, minus V3. Again jump and look backward. What is the sign? Positive, plus V4. Jump and again look backward. What is the sign? Negative, minus V5. Now what is the potential? 0. Here we have reached, right? Now what is the potential of this point? 0. Ground means 0 potential. Okay? Ground means 0 potential. We started from here and reached at this point. 0, jump, V1, jump, minus V2, jump, minus V3, jump, V4, jump, minus V5. And what is the, we have reached till this point, and what is the potential of this point? That is equals to 0. So basically here, V1 plus V4 is equals to V2 plus V3 plus V5. Did you understand this? Very basic thing, well and good. Okay, just start from a point, keep on jumping, and then just write the potential at the point that where you reach. Okay, now you need to apply KCL and KVL in, I guess I missed something. Okay, no, now you need to apply KCL KVL in, sorry, KVL in these problems. Okay, so how will you do? The ground is already given, this is ground, so from here you jump VA, again jump minus V1, again jump minus V2. At what point you reached? At this point. What is the potential of this point? 0. So VA is equals to V1 plus V2. Started from here, jumped it, VA, jumped again, minus V1, jumped again, minus V2 equals to 0. Now talking about this point, talking about this, you started from here. Now this, like in most of the problem you will see, they will just make a dot and write VA. What does that mean? That means that it is the same as before. It is same like this. VA means potential from ground. So there is a battery of VA point from here to here. What is the potential? From here to here, what is the potential? VA. From here you will jump and see the sign. It is VA only. So it is plus VA only. So this can be made like this only. Are you getting my point? What does that VA mean? That VA means from ground to potential of that point is VA. From ground to potential of that point is VA. Okay. Sorry, this is V1 and this is V2. So it is the same as this. So again, VA minus V1 minus V2 equals to 0. So VA is equals to V1 plus V2. Right? Now talking about this. From here to here you will jump VA minus from here to here. From here to here you jumped, look backward, positive sign. Again jumped, look backward, negative sign, minus V1. Again jumped, look backward, negative sign, minus V1. Now, what is the potential of this point? The potential of this point is VA minus V1 minus V2. You wrote it. And if you start from here, jump VB. From here to here you jumped. From here to here you jumped and look backward. What is the sign? VB. So what is the potential of this point? That is equals to VB. Or what you can do? You can simply follow the same procedure. Okay. From here you jumped VA minus V1 minus V2 minus VB equals to 0. VA minus V1 minus V2 and here minus VB equals to 0. So again you will get this only. So for this point I will write it like this only, minus VB, and here you reached, and what is the potential of this point? That is equals to 0. So equals to 0. So VA is equals to V1 plus V2 plus VB. Right? Now talk about this. Try writing on your own. How will we start? Now, if we want to make the circuit of this, tell me how should it look? In like you are studying it initially only. This is very first lecture of yours, so that's why we are making the circuit. When you will be comfortable with all these circuits now, then you don't need to make the circuit again and again like this. Okay, you will be easily writing all the equations and everything. अभी के लिए बना के देख लो, बाद में अपने आप धीरे धीरे समझ में आ जाएगा. तो ऐसे ही बनेगा. That's how we will make it from here to here VA potential, and at this side from 0 to this potential, that will be VB. So basically, if we are showing this potential, what is the value of this potential? VA. And what is the value of this potential? VB. From 0 to this point, that will be VB. And from here to here, what is the value of this potential? VB plus V2. From here to here, VB plus V2. And from here to here, it will be VA minus V1. So basically, if we want to write the value of this potential, it can be VA minus V1, or it can be VB plus V2. So from here as well, you can write VA is equals to V1 plus V2 plus VB. So basically, that thing that I told you about starting from a point and then jumping, that you can do for any arbitrary point. You started from here, 0 minus VB plus V2 plus V1. Like what I am saying, you start from here, VB, then again jumped, plus V2, then again jumped, plus V1. That is equals to VA. Okay, so again this formula is coming, VA equals to V1 plus V2 plus VB. So at any arbitrary point, you can try applying this thing. Okay, just start from any point and keep on jumping. Okay, so that's how you can write the equations, right? So I hope you have understood the concept of KVL as well. So basically KCL, KVL we have studied, and then we just saw the some basic terms of node, branches and everything. So this is what we covered in 15-16 minutes. So KCL, KVL, and then these basic things. Okay, now let's move on to the classification of elements. So there are mainly 5 types. There can be many kind of classification, but mainly these many types are there: linear and linear versus non-linear, then active versus passive, then lumped versus distributed, then unilateral, bilateral, and then time variant and time invariant. Okay, so these things we will study. So let's start from linear and non-linear element. So what are the linear elements? So for linear element, relationship between I and V is linear. So what do you understand by this? So basically, if you draw the IV characteristics, what are the IV characteristics? What are the IV characteristics? The response of current with respect to the change in voltage, that is known as IV characteristics. The response of current with respect to changing voltage. So at y-axis we will make I, and at x-axis we will make V. So basically, how your current is getting changed with respect to the change in voltage. So that's how it should look. So that's how the IV characteristics look. So what should be the example of all these things? Tell me. Resistor. For resistor, if you haven't studied, then we will study. If you have studied, then it's good. V equals to IR. Okay. For inductor, V is equals to L di by dt. For capacitor, V is equals to 1 by C integration I dot dt minus infinity to t v. Okay, so one important thing here is that integrator and differentiator are linear operator. Okay, integrator and this thing you need to remember, and differentiator are linear operator. So basically, if you draw V versus I characteristics, I versus V characteristics of inductor and capacitor, then only you will get a straight line like this. So for linear elements, IV or VI characteristics is a straight line passing through origin. That thing you need to remember. Okay, straight line passing through origin. So basic thing is that if V is increasing, your current should always increase. If V is increasing in negative direction, your current should increase in negative direction. Okay, if your V is increasing in positive direction, your current should increase in positive direction. That's it. This is what a linear element is. So basic linear elements are resistor, inductor and capacitor. Okay, that we studied in 11th, 12th class. Okay, now moving on to the non-linear elements. So in non-linear elements, what do you think what will happen? The VI characteristics or IV characteristics? I will write it down with pausing the video. So basically in this case, relationship between I and V is non-linear. Let's just make a graph. Let's call it I and V. Any arbitrary graph we are making. Okay. So I'm making the graph something look like this. If V is increasing, the current is V is increasing in positive direction, the current is also increasing in positive direction. Now if V is increasing in negative direction, but the current is increasing in positive direction. So it's not a straight line passing through origin. It's not a straight line passing through origin. If it was a straight line passing through origin, it would look something like this. Okay. So it's not a linear, it's not a linear element. Okay. So relationship between I and V is non-linear. Now let's see some examples. Let's take example of diode. If anyone remembers this equation, what is the current equation of diode? If you don't remember, no need to worry. It is basically ID equals to I naught e to the power V upon Vt. So let's just make it like this. This is a diode and this is the voltage V. And this is the current ID that is flowing. So this is a reverse saturation current e to the power V by Vt. So if we make the IV characteristic of a diode, how does it look like? It looks something like this. It will be 0, then it will go on like this. 0, then go on like this. Okay. So this is basically ID versus voltage. Okay. We call it VT. VT. Okay. No, this is not VT. Sorry. This is V gamma. Built-in potentialities. Okay. And talking about the reverse bias, there is always a reverse saturation current. So this is how the characteristic look like. Right? It is not a linear relationship. There is no linear relationship between these two. This is an exponential equation. Right? This is exponential. Exponential. In deeply, you will understand it in analog electronics. I will teach diode circuit very deeply in analog electronics. But for network analysis, this is just an example. Like in diode, there is no linear relation. Similarly, in BJT and MOSFET also, there is no linear relation. Okay. So example 1 is diode, then BJT, and then MOSFET. BJT and third is MOSFET. So in for these two devices as well, the current equation is not like that. If you write the current equation of MOSFET, it is like some constant VGS minus VT whole square. That's for saturation region. You don't need to worry what is saturation region, what is linear region or anything. But this is how the characteristics look like for MOSFET. Okay, and it is something like this for. Can I do here? You don't need to mug it up. I'm just giving you the examples. Okay, so basically this is how the characteristics look like, and V versus I curve is not linear. So these are the example of non-linear elements, and these were the example of linear elements. Okay, so for non-linear elements, IV or VI curve is non-linear. Okay, very simple thing. Well and good. So you have understood the concept of linear and non-linear elements. So it will be used many times while studying the complete EC through your BTech or everything. It will be used many times. Linear element, non-linear element, linear system, non-linear system. Okay. So about the system you will study in signal systems. Okay. In signal system you will study what is a linear system, what is a non-linear system. But talking about the element, I have told you these things. Okay. So these are the basic things about linear and non-linear elements. Okay. Let's move on to the next thing, that is active element and passive element. This is also a very important concept. Okay, so what are the active elements? So first point, elements that delivers energy. Elements that delivers energy. For them, the impedance can be positive or negative. That delivers energy for infinitely long time. This is important thing. For infinitely long time. This is very important thing. Infinitely long time. What is the other thing? Impedance can be positive or negative. It can be positive or negative. Okay. Third thing, has the ability of internal amplification. Okay. Now, initially you wouldn't be able to understand all these things. Okay. So let's see some example. Like there is one IC that is known as op-amp. You will study about it in analog electronics. This is known. This is called as op-amp. There are transistors like BJT, MOSFET, JFET. About all these things you will study in analog electronics. So these are these things that can deliver energy. Okay, they can deliver energy, and op-amp can deliver energy, and they have the ability of internal amplification. What does that internal amplification mean? Suppose you are applying a input of 2 sin omega t millivolt. Okay, you are applying an input of 2 sin omega t millivolt. Now they can give you the output of 10 sin omega t millivolt. Okay, this is what known as amplification. कम वोल्टेज अप्लाई किया, ज्यादा मिला. You applied 5 volt to an op amp, you can get 100 volt as an output. So it has a gain of 20. From 5 to 100 we go. So from 5 to 100 uh, we went. So we have a gain of 20 there. So this is known as an internal amplification. So all these devices has the ability of internal amplification. Okay. I will just make a basic circuitry of an op amp. So no need to make the basic circuitry of op amp here. You will eventually understand everything when you study about these elements. So in this mainly in network analysis part, we will study about the passive elements, so that we will study further. And in analog electronics part, we will study about the active elements. Okay, about transistor, op amp, and everything. Okay, understood? Let's move on to this. What are the passive elements? I will write down the points pausing the video. Okay. Yeah. So these are the points for passive elements. They absorb energy. They have an impedance of positive, only positive. It can't be negative. In case of active element, it can be positive or it can be negative. But in case of passive elements, it strictly has to be positive, and it doesn't have the ability of internal amplification. Now we will understand these points. So example are resistor, capacitor, and inductor. Okay, so what do I mean by the impedance has to be positive? Okay, fine. Element that absorb energy, that is also fine. What do I mean by internal amplification? That means, like, if I connect two resistors like this. Okay, let's call this one R1 and this one R2, and I apply V in here, and then this is your V0. So V0 will be your R2 upon R2 plus R1 into V in. What do you think? What is the gain now? If I apply a 5 volt input, can I get higher than 5 volt? At output, can I get higher than 5 volt? Using a transistor, using a resistor, can I get an output higher than 5 volt? If I have an input of 5 volt, can I get output higher than 5 volt? Only using resistors or capacitors or inductor? No. Here V0 is R2 upon R2 plus R1. Let's assume R2 is 2, R1 is also 2. So 2 upon 2, 2 plus 2 into V in. So V0 will be V in by 2. If you don't know how I wrote it, you will understand it. I will teach you that. Just for example, right now I am writing. So there is no amplification. No amplification. Okay, so basically there is no ability of amplification. So if we draw the characteristics for VI characteristic, if we draw for passive elements, so how should it look like? It can look V, the impedance has to be positive. What does that mean? Impedance has to be positive. What is impedance? Impedance is V by I. That has to be positive. What is impedance? Impedance is V by I. Okay, that has to be positive. So in this quadrant, it will be positive, right? Positive by positive, it is positive. And in this quadrant, it will be positive. Okay, I forgot to make what is. Let's assume this is I, this is V. So here V is positive, I is positive. Yeah. So in first quadrant, it will be positive. So yeah, it can be a passive element. Now talk about this quadrant. It will be positive or negative? It will be negative because here I is positive but V is negative. Now talk about this quadrant. I is positive, V is sorry, I is negative, V is also negative. So negative by negative, it will be positive. So yeah, there also we can have passive elements. Okay, and here it will be negative because V is positive and I is negative, so it will be negative. So only in first and third quadrant we can have passive elements. And talking about this, talking about active elements, we can have those in any quadrants. Like if there is a circuitry, if there is a IV characteristic like this, so for this your Z is positive, and for this your Z is negative. So yeah, it can deliver the energy. If Z is negative, it can deliver the energy, so it will be counted as active elements. Here your Z is positive. Here strictly your Z is positive. Okay, even at a single point your Z can go negative, then it will be counted as active element. Even at a single point, if your Z can go to negative, it will be counted as active element. But here strictly your Z is positive only, so it will be counted as passive elements. So passive elements are those who absorb energy. They are not active. Active elements are active. They can deliver the energy. Okay, so that's the concept. Now sometimes what happens is that, like, note, you will understand this thing deeply in transient analysis. But if capacitors and inductors are initially charged, they can behave as active element. They can deliver energy for some time. They can deliver energy for some time, but not for long time. Okay, like just let's assume that you don't know this concept deeply, but let's assume your capacitor is charged to 5 volt, and this is your circuit, this is a resistor R. So it can deliver energy to this resistor. Okay, this capacitor can deliver energy to this resistor, but not for infinitely long time. It will be discharged to 0 volt in some after some time. That's why I wrote in this definition that elements that deliver energy for infinitely long time, they will always deliver energy. Like voltage, op-amp, transistor, voltage source, current source. You must have studied about those. Voltage source, or we will study as well. Voltage source that gives voltage, current source. Okay, so they deliver the energy. Okay, so this is one important point. Like sometimes you may get it out like here the capacitor is delivering the energy, so why don't we call it an active element? Because it doesn't always deliver the energy. Okay, it has to deliver the energy every time, then only it will be called as passive element. But it's not it is deliver the energy for a very short time. Okay, so it will always be counted as passive elements only. Okay, so let's move on to this third classification, that is lumped and distributed. So it is a very important, and like most of the times people get it wrong. So what are the lumped elements? So if you can read the definition. So in lumped element, like the complete property of an element will be distributed at one point. Okay, let's assume that you have this very long wire, So like the complete, let's assume it has all the components R, L and C. So the complete property of R can be distributed at one single point, then L and then C. So you can distinguish, yeah, this is the portion of R, this is the portion of L, this is the portion of C. So this is what I have written, that concentrated in one place or located in smaller space in a circuit. Okay, and lumped elements can be physically separated from the circuit for analysis purpose. Like you can separate resistance from here, you can separate inductance from here, you can separate the capacitance from here. So these are called lumped element. So whatever the circuit we have shown here now, this is also a lumped element. Okay, whatever the circuit we have seen, these all are lumped elements. Resistor lumped element, lumped elements. Okay, so all these are lumped elements. Okay. In the above circuit, it can be seen that the resistor, capacitor, and inductors are located at a single point, and all the elements can be separated from the circuit. Okay, so this is known as lumped elements. Now, what are the distributed elements? So here you will not study about it. Also, you will not study about it in analog electronics. But when you study the EMFT topic and when you study about the transmission line in power system, you will study about the transmission line, and in EMFT you will study about the transmission line. So when you study that, you will get to know there is a term called transmission line. Okay, so in transmission line, like there are mainly four components: RLGC. Okay, I guess you can't see the complete definition here. I will just read it out. So all the elements are distributed along the wire. Okay, along the line. So in this diagram, you can see these are the transmission line. Okay, this is the transmission line. This is the transmission line. So here you can't really separate out what is what is R, what is L, what is G, what is C. It is distributed along the line. Okay, so and circuit element that is assumed to be distributed across the entire length of the circuit is called distributed element. And unlike lumped element, distributed element are not concentrated as at a single point. Distributed elements cannot be separated from the circuit since they are distributed everywhere in the circuit. Okay, so in the complete circuit there are R, L and GC at different points, so you can't really separate them out. Okay, so a transmission line is the best example of a distributed circuit. In transmission line, the components like resistors, capacitors and inductors are distributed along its length, which cannot be separated. So when you study about the transmission line, you will see it in a deep manner, where what you will do for doing the circuit analysis, what you will do, you will just get the resistance at delta z length. Okay, you will get the resistance at delta z length and call it R into del z. Okay, then you will get a inductor at inductance at delta z point, and then you will call it L into del z. Okay, then you will get a capacitance, you will call it C into del z, and then uh, this conductance C into del z, and that's how you analyze the circuit. Okay, you will study deeply it in the chapter of transmission line. Okay, so this is what is known as distributed elements. Okay, let's move on to the next point, that is unilateral and bilateral. Okay, this is also a very interesting property, sorry, very interesting classification. Okay, so what is known as bilateral elements? So bilateral elements are those which can allow the current in both of the direction. Okay, they allow the current in both of the direction. Let's uh, see some example. Let's see the example of resistor. Okay, so this is a resistor. So the current can flow in this direction as well, right? The current can flow in opposite direction as well, in this direction as well. This is R, this is R. If the current is flowing in this direction, we will write it like this. We will see the sign. Okay, in later part of the chapter, we will see it. But yeah, so that's how you can write V equals to IR. Here also V is equals to IR. So the current can flow in this direction as well and in this direction as well. In both of the direction, the current can flow. Similarly, for inductor and capacitors, the current can flow in both of the direction. Okay, understood? Now, what is unilateral? It allows current in one specific direction only. Okay, so examples are like this. What are the examples? Like, take a diode. Okay, this has a potential V like this. So the current in this direction will be finite. right? The current in this direction can flow, but in the diode, the current in this direction will be nearly 0 ampere, not 0 ampere, nearly 0 ampere. So it doesn't allow the current in this direction, but in this direction. So it is unilateral element, allows the flow of current in only one direction. Okay. So example is diode. Other examples are, you will study about them, BJT and MOSFETs. They also allow current in one specific direction. In NMOS, you can see the current flow from drain to source, and in PMOS, you can see the current flow from source to drain. And in BJT as well, you can see the current flow from collector to emitter only. Okay. So yeah. So this is collector to emitter and some base current. So they have the specific direction of current flow. Okay, you can't really change the direction of current flow in these devices like diode, BJT, and MOSFETs. Okay. So now talking about the IV characteristics. So we will write down a point. IV characteristics or VI characteristics for bilateral elements are symmetric about origin. Okay, so what do you mean symmetric about origin? So let's make this IV characteristics. This is I, this is V. So this is symmetric about origin. So how do you check the symmetry about origin? So what you will do, you will just place a mirror at this point like this. You will place a mirror like this. Okay, so just placing a mirror like this. So from here to here, what do you see? This line. And from here to here, what do you see? This line. So both of them, so this is symmetric about origin. Okay, or I and V. Like this if I make. Okay, this is how now I have replaced the mirror like this. So this is also symmetric about origin. Okay, so these are symmetric about origin. Now talking about unilateral element, they are not symmetric about origin. Now tell me, this curve is symmetric about origin or not? This is I, this is V. So is this symmetric about origin? No. Try replacing the mirror like this. In any direction you try to replace the mirror, but it should be between the axes. Like you can't really place the mirror like this. No. It should be between the axes. Okay. So try replacing the mirror like this. So from this side you will get this kind of curve. At this side you are not even getting any curve. So this is not symmetric about origin. Or try replacing the mirror like this or like this. So at this side you are getting this curve, but at this side you are not even getting any curve. So this is not symmetric about origin. Or how you can check? What is the value of Z here? Z is positive. And what is the sign of Z here? Z is negative. So at one side you are getting Z positive, at one side you are getting Z negative. So this is not symmetric about origin. In this you see Z is positive, Z is here also Z is positive. Here Z is negative, here Z is negative. And also both of them should have the same slope. Okay, the slope should also be same, like this slope and this slope should be same. Okay, so both of them should have a same slope. This slope and this slope should be same. Okay, so both of them are having the same slope and the sign of the impedance is also the same, then only it will be called as a bilateral element. It should be perfectly symmetric. Like you replace the mirror like this or like this, it should have a perfect symmetry. Here you can see it has a perfect symmetry, but here there is no symmetry. Okay, so this is IV characteristics. Okay. That's how you can differentiate. So let's revise it once again, whatever we have studied in the classification. First, we study about the linear and non-linear element. For linear element, it should be a straight line passing through the origin. So the relationship between I and V are linear. V equals to IR, V equals to LdI by dt, and V equals to 1 by C integration I dot dt. Then we study about the non-linear element. In non-linear element, the relationship between I and V is not a straight line passing through origin. Here you can see in the diode there is the current like there is this relation. So this is not linear at all. Okay, and in MOSFET and BJT also there is no linear relationship that we will study in analog electronics. Now coming to the active elements and passive elements, active elements are those which can deliver the energy for a infinitely long time. It has the ability of internal amplification as well, and for them z can be positive or negative. So when we draw the characteristics, here z is positive, here z is also negative. So anytime the z is becoming negative, that means it has the ability of delivering the energy. So it can be treated as as an active element. For passive elements, it has the ability of uh, observing the energy. Okay, and the impedance for them will always be positive. Strictly, it will always be positive. Okay, like inductor, capacitor, and resistors. Okay, and there is no amplification. Okay, and there is one note is that like sometimes the inductor and capacitor may deliver the energy, but not for the infinitely long time. So they are always counted as an passive elements only, not as an active element. Okay. So, and then we study about the lumped and distributed. Lumped means all the property of some particular element that is distributed at only one point, and you can separate them out: resistance, inductance, and capacitance. Okay, like that. And in distributed element, the property of an particular element is distributed all along the line, like in transmission line. So it is distributed all along the line, like RLCC. Then we study about the bilateral element. It allows the current flow in both of the direction, positive and negative. In resistor, we can flow the current in this direction and in this direction. Same with inductor and capacitors. Okay. And for the IV characteristic symmetric about the origin, not about any axis. It is symmetric about the origin. So you have to place the mirror like this or like this. So then you can see it is symmetric about the origin. Also, the sign of impedance is also the same. Also, the slope is same. So the sign of impedance is same. The slope is also same. And in case of unilateral element, it is not symmetric about the origin. Okay. So if you place the mirror like this or like this, you don't get any symmetry. So it is no symmetric about the origin. So these are the elements we have studied. Now finally we will study about time variant and time invariant. Okay. So time variant, what does that mean? IV characteristics varies with time. Uh, Time variant varies with time. And time invariant IV characteristics doesn't vary with time. We are covering anything that can be asked, every single point, and we will solve many questions. When we come to question, you will realize it. We will solve many questions. IV characteristic doesn't vary with time. Okay. So there are no particular example like that. This like I can't really say that resistance will always be a time invariant system. Sorry, a time invariant element. I can't really say that. It can sometimes it can behave as a time variant, sometimes it can behave as a time invariant. Okay. So what do we really mean by that is like this is the IV characteristics now. So you make a IV characteristics at time t1. Okay. Then next day you come at time t1. Then next day you come and again make the characteristics. The characteristic is same. The next day you come again make the characteristics. The characteristics is always same for time t1, t2, t3, and t4. For every day you get the same characteristics. Then it will be called as time invariant. Okay. What do you mean by time variant? You make a characteristic at some day. This is IV characteristics. Okay. So you make this characteristic at time t1. The next day you come time t1. Why am I writing time t2? The next day you come, the characteristics make like this, looks like this. So this is time t2. So for time t2 you get this characteristic. For time t1 you get this characteristic. For time t3 you will get some other characteristics. Okay. This is like this only. Okay. So this is time variant and this is time invariant. I can't really write down an example that register will always behave as time invariant. Sometimes it can behave as time invariant, variant or invariant as well. Okay, so we can't really make a certain example. Okay, now we will see a question that is a very interesting question. Okay, so you need to characterize the element that are given below. Okay, so you need to tell me whether it is linear or non-linear, whether it is bilateral or unilateral. Okay, and we can't really say time variant or invariant based upon the characteristics, right? There is one characteristic drawn, so we can't really tell it is time variant or invariant. So you need to tell linear, non-linear, unilateral, bilateral, and what else you will tell? And you will tell active and passive. So these three you will tell: active, passive, linear, non-linear, and unilateral and bilateral. Okay, so based on this circuit, you should try solving it on your own. Just write down your answer, then check it. Okay. Okay, before going into that problem, I need to clear one thing. Like, some student may have some doubt. Like, in unilateral elements, what did I tell, that the current allows flow in one particular direction only. So here your V is negative, still there is some current. Yeah, there can be some current. Okay, so like the main purpose here is that, like, if V is positive, the value of current is like that. If V is negative, the value of current should be like this. If V is increasing in negative direction, the current should increase in negative direction, then only it will be called as bilateral element. So in the definition of bilateral element, I have written that current allows the current in same direction but offer the same impedance in either direction of the current flow. The value of impedance should be the same, the slope should be the same. Okay, here the slope are different. Here the slope is positive and here the slope is negative. So all the elements that are not bidirectional or bilateral, they will be known as unilateral. Okay, all that elements that are not bilateral, they will be known as unilateral. And what is the definition of bilateral? That allows the current flow in both of the direction and offer the same impedance. Okay, that's why I say that it should be symmetric about the origin. They are offering the same impedance. Here the value of z and here the value of z are same. Sign is also same. Okay, the slope is same and sign is also same. Okay, so some may get this doubt. I just now thought about it. So let's move on to this. Let's talk about unilateral and bilateral only. So is it symmetric about the origin? No, it's not symmetric about the origin. So it is unilateral. Tell me about this. Is it symmetric about origin? Yeah, it is symmetric about origin. It is bilateral. Tell me about the other one. Is it symmetric about the origin? No, it is not. Here the value of z is 1. Here the value of z is, this is v by I. So v value is 3. So here the value of z is what? 3 by 4. Here the value of z is z equals to 1 and 3 by 4. That means it is not bilateral. That means it is unilateral. Unilateral. Talk about active and passive. Tell me, is it active or passive? Passive. Why so? Because z is negative. Tell me, is this active or passive? It is active. Why so? Because z is always positive. It is active or passive? It is active. Because z is always positive. Z is always positive here, right? What is the value of z here? At this point. At this point. What is the value of z? Tell me, what is the value of z? With change in I, there is no change in voltage. So here the value of z is 0. Z can be written as the change in voltage with respect to the change in current. So there is no change in voltage with respect to the change in current. So it is 0. Okay. There is no slope basically. If there is slope, then we can write V by I is equals to 1. If there is no slope, then it will be 0 only. So here also Z is 0. Right. So always Z is positive or 0, or here also it is positive or 0. So it is active element. Okay. Now talk about linearity and non-linearity. Tell me, if it is linear, straight line passing through origin. Is it there a straight line passing through origin? No. So it is non-linear. Okay. Tell me about the other one. Is it linear? Think about it and tell me. Straight line passing through origin. Yeah, straight line passing through origin. But here, what is happening? here it is not a straight line passing through origin. Na? It has to be always straight line passing through origin. So only for I equals to minus 4 to 4, it is acting as a linear element. After that, it is not acting as a linear element. Okay. So it is also considered as non-linear. Did you understand it? Straight line passing through origin for minus 4 to 4 only. Not after 4 and minus 4. Not after or before 4 and minus 4. So the straight line passing through origin should always be there. Similarly for this as well, this is also non-linear because straight line passing through origin is not always there. Okay, so this is also known as non-linear element. Okay, so did you understand it? There is one note you can also write down. Here I can write it down. All the linear elements are bilateral. Did you understand this point? All the linear elements are bilateral. What are the linear elements? Like this or like this. So are they symmetric about origin? Yeah, they are symmetric about origin. So all the linear elements are bilateral, but not all bilateral are linear. This is bilateral, but this is not linear. This is non-linear. Okay. So not all the bilaterals are linear, but all the linear elements are bilateral for sure. Okay. So this point you have also understood. So now we have covered this classification and KCL KVL. Basic KCL KVL we have covered and classification we have covered in the last 1 hour. Okay. I hope you have understood the concept. Basic definition, then KCL KVL, then the classification. Okay, active passive. Just revise it once. It will be all clear to you. It will be in your mind. They don't really ask direct question from that, but if they ask, they can frame very good question. Okay, and many of the student, even the teachers, don't focus on this point. Okay, they should teach this point because these names are again and again used, especially these active elements, nonlinear element, active passive, linear, nonlinear. These terms you will see in the complete analog and network analysis. Like this is active element, active filter, passive filter. Like people talk about that we are studying active filters using op amp. So why do we call it active? They don't even know that. So now you know why do we call that those filter active filters, because they can deliver the energy. Okay, so those elements that can deliver the energy, they are known as active filters. So active elements. Okay, so basically we will study about all these things. So slowly we are moving in the chapter. Now in from the next chapter we will study about the basic Ohm's law. Then we will study about resistor. We will see some questions, capacitor, inductance. Okay, and then we will solve many problems. Then we will study about the energy and everything. So in the next chapter we will study all that. Okay, thank you.